The time has come, the walrus said, to speak of vector spaces. We're going to start chapter 2 now, and this is a bit of a change of pace. We're going to be talking about the abstract theory of vector spaces. I apologize for my hoarse voice. I'm recovering from a cold. Probably someday I'll have to go back and redo at least the audio on these couple of lectures. So you're all familiar with Rn. So Rn is a bunch of vectors, and each vector is an n-tuple of real numbers. And we're all familiar with drawing R2, for example, and vectors are written like this. And you all know about adding vectors. And other properties of Rn. And the notion of a general vector space is an abstraction of these properties that Rn has. So what are those properties? Let's go over the definition of a vector space. So a vector space is a set, a collection of things, with two operations, one called plus and another called times. And first I'm just going to tell you what these operations do. So I'm always going to write V and W for things in V, which are called vectors, and R and S for numbers or scalars, real numbers. And I'm going to use sort of shorthand here. If V and W are vectors, then so is V plus W. And if R is a scalar and V is a vector, then so is R times V. So this is shorthand for saying that the operation of addition is defined on two vectors, and the operation of scalar multiplication is defined on a scalar and a vector. And then the properties that these operations have are all the familiar ones from Rn. So there's the commutative law, V plus W is the same as W plus V. The associative law, you can group things however you want. There's a zero vector, which you can add to any vector and get itself again. There's the minus vector, which you can add to get zero. There are two kinds of distributive laws. This one says if you add two scalars and multiply times a vector, that's the same as multiplying the first scalar times the vector plus the second. And similarly, if you multiply a scalar times the sum of two vectors, you can also write it this way. And then the last one is the distributive property of scalar multiplication. Oops, this is a misprint. This should say Rs times V is R times S times V. Okay, that was, I know, sort of quick, but these are all stated clearly in the book. And I'm going to go on and talk about some other properties of vector spaces. All of these properties are familiar to you in the case of Rn. Let's look at a couple of them as examples. So, for example, consider the commutative law, V plus W is equal to W plus V. And what I'd like you to do when we're going through these is think about what it is about the underlying structure which makes this true, and how this might be true in different settings. I'll mention what I mean by that in a moment. So consider this identity. Well, if you write this out, it says that A1 through AN plus B1 through Bn is supposed to be equal to the same thing in the other order. Well, this side looks like A1 plus B1 and so on, and this side looks like B1 plus A1 and so on. And the fact that these two are equal comes down to the fact that these two are equal in each coordinate. And in other words, it's just the corresponding property for the real numbers that A plus B
is equal to B plus A.
And this is what I mean about thinking more generally. We can define vector spaces over other things besides R, like the complex numbers. And since the complex numbers have this property, the corresponding vector spaces will have this property. But we'll see occasionally that there are certain things which can break down if you're not careful. Another good thing to do with these properties is to think about them geometrically. And the geometric intuition is often very useful. So let's look at the commutative property of vectors in terms of adding vectors visually. So the way you add two vectors is you take a vector v, and to add it to another vector w, you put them head to tail like this, and the sum is this vector right here. That's v plus w. On the other hand, if you added them in the other order, you would first do w, and then do v, and that's the vector w plus v, and since they both wind up in the same point here, that says that v plus w is equal to w plus v. And let's look just very briefly at a little what scalar multiplication means. So if you have a vector v, multiplying it by a scalar stretches it. So for example, if you were to multiply it by 2, this would be the vector 2v. And if you were to multiply it by minus 2, that would be in the opposite direction. This is the vector minus 2v. And I should say now that I'm going to often drop the times notation. So instead of writing r times v, I'll just write rv. So instead of writing 2 times v, I'm just going to write 2v. Now, let's check something here. I wrote minus 2v. What do I mean by that? Where's the minus? Do I mean minus 2v? Or do I mean minus 2 times v? Or to, let's see, which is it? Well, if you really write this out carefully, what I'm saying, this is minus 1 times 2 times v. Whereas this is minus 1 times 2 times v. And these two things are equal by one of the rules, the associativity of scalar multiplication. So it doesn't matter which way you think of it. Okay, I'd like to look at a bunch of examples of vector spaces. And before I do that, let me just say a word about that. The most familiar example, of course, is Rn, which is written as the set of n tuples, where the AIs are real numbers. Oops. And this is by far the most important vector space, but there are other vector spaces which occur, so to speak, in nature, for example, when solving differential equations, which arise naturally as vector spaces, but not necessarily just in the form Rn. And one of the important things to do is to learn to think a little bit abstractly. It's sort of nice to have Rn to go back to as an aid, but it's helpful to get away from Rn when you can and just think of vector spaces as abstract objects. So let's look at some examples of what I mean by that. So basic example, and an important one, is sometimes written as Pn, which is, this is the set of polynomials
of degree less than or equal to n. So what does that mean? That's the set of things of the form a0 plus a1 times x plus dot 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 a n x to the n, where the ai's are real numbers and x is an indeterminate. And when to say that this is a vector space is to say that it has two operations on it, plus and times, and it's the usual operations that you're familiar with for adding polynomials and scalar multiplication of polynomials. So, for example, 1 plus x squared plus 2 plus 3x is equal to 3 plus 3x plus x squared. And this is all going on inside what? P2. This is a polynomial of degree less than or equal to 2. So is this, and so is that. And similarly, if you multiply 2 times 1 plus x squared in the usual algebra, you get 2 plus 2x squared. Okay, let's look at another example. This one's very much in the spirit of some things we'll be doing later in the course. Let V be the following set. It's the set of functions f of x satisfying the equation d squared f of x dx squared is equal to minus f of x.
These are functions whose second derivative are minus itself. I claim this is a vector space.
So why is this a vector space?
Well, can you think of any functions which satisfy this?
If you think about it for a minute, I think you'll see that one possibility would be to take f of x is equal to cosine of x, because the second derivative of cosine is minus cosine. And another possibility would be to take g of x is equal to sine of x, also has this property.
Now, can you think of any other functions which satisfy this?
Well, I claim that this thing is a vector space, so if that's true, you should be able to add these two functions. You should be able to take, let's take capital F to be, for example, cosine x plus sine of x. Does this work? Well, let's see. F prime of x is equal to minus sine of x plus cosine of x, and f double prime is equal to minus cosine of x minus sine of x. And just looking at the signs here, you see that indeed this is equal to minus f of x. And more generally, if you look at f of x is equal to anything times cosine of x plus anything else times sine of x, then f prime is equal to minus a sine plus b cosine. and f double prime is minus a cosine minus b sine. So if you just look at this calculation, this a just came along for the ride. Nothing happened to it the whole way. And since cosine goes to minus cosine, when you multiply it by a times cosine goes to minus a times cosine, and similarly the b term. And that's a confirmation that you're allowed to take sums of these two functions, and in fact you can see that these are all of the solutions. In fact, v is exactly the set of functions of the form a cosine x plus b sine of x.
That is to say, once you put some mild assumption on the functions. And so this is what I mean by a little bit of a change of point of view. This is a very simple example. All I gave you was a differential equation, f double prime is equal to minus f, and out popped the vector space. And the fact is that you can write any solution to that equation as a linear combination, something times this function plus something times that function. And really all that matters here is you have an a and a b. And this vector space is essentially R2. It's a two-dimensional vector space. I'll write this down. V is a two-dimensional vector space. And as such, it's said to be isomorphic to R2. And I'm not going to explain exactly what I mean by that right now, but that is to say you can think of it as being R2, and if you identify this function with this pair of numbers a plus b, and if you add these functions here, that's just like adding these vectors a and b. And this is a general property of a certain class of differential equations. The set of solutions of these differential equations are automatically vector spaces. And the fact that they have this vector space structure and properties of those vector spaces is essential to thinking about them.
Now, here's a somewhat different kind of example, related but a little bit different. Let's let v be the set of all functions from R to R. That is to say, any function that you can think of that takes real numbers to real numbers, like e to the x, or 1 plus x, or whatever.
I claim this is a vector space.
Well, what does that mean? I have to tell you how to add functions. So suppose you have two functions, f1 and f2. What do I mean by f1 plus f2? This is supposed to be a new function. And it is, and it's what function is it? It's the function. It takes the value at the real number x. It takes the value f1 of x plus f2 of x. The usual thing, e to the x plus 1 plus x, is just kind of a tautology, e to the x plus 1 plus x. Not much to say here, except that to notice that this law, which might look sort of weird and formal or something, is really what's behind this identity. And what is scalar multiplication? If I have a scalar and I multiply it times a function, I'm supposed to get a new function. So I have to tell you what its value is at a point x, and the answer is it's r times f of x. So this is a real number, and this is a real number. And so when you multiply two real numbers, you get another real number.
So it's pretty straightforward to check that all of the formal properties of vector spaces hold here. Commutative, distributive, and so on.
So for example, what's the zero vector in this vector space? What do I mean by that? This is supposed to be a function such that if you add it to any other function, you get itself again. Gee, what is that? Well, the function, I'll write it with an arrow to indicate this is a vector. It's supposed to be a function which takes a real number x to some scalar. What scalar would you like to take? Well, obviously the scalar 0. Right? So that is to say f of x is just the zero function, but you got to be a little careful how you think about it. It's really a function which takes any real number to 0. So, for example, to say that f plus 0, excuse me, I don't need this or this, to say that if f is any function, I'm claiming that f plus 0 is equal to f. What does that mean? That says that f plus 0 at any point x is supposed to equal f of x. Well, what is f plus 0 of x? Let me write that up here. By definition, that's f of x plus 0 evaluated at x. And that is certainly 0. That's how I took it. And so this is true. These two are equal.
So that's kind of a silly formal little check that seems maybe pointless to you. But this is the kind of thing that you should get used to doing because other examples like this come up, and sometimes surprisingly subtle things can happen.
And one last comment in this section. What is the additive inverse? What is minus f? Well, minus f of x is just minus f of x. Minus f of x is, by definition, minus f of x.
Sort of obvious. If f is a function, minus f is a new function. And what does it do? It takes any x to not f of x, but to minus that number. And with these operations, you can check that this is a vector space.
Now, there's one very special and there's one very important property of this vector space, and that's the following. So we're still talking about this space of all functions from from R to R.
This is a vector space.
What's its dimension? Well, we haven't defined dimension yet, but I gave you an example before. The one involving solutions of the differential equation f double prime is equal to minus f. There were essentially two functions, cosine and sine, and the dimension was 2. So how many different functions are there from R to R? Well, if you think about it for a minute, it's clearly not finite. The dimension, however, once we define it, is clearly not going to be finite. This is an infinite dimensional vector space.
And there's a huge distinction between infinite dimensional vector spaces and finite dimensional vector spaces.
And in this course, we're going to be talking almost exclusively about finite dimensional. Occasionally, I'll mention infinite dimensional things. Maybe I'll say W here. In this course, we're going to be focusing on the case when the dimension is finite.
And you should be a little wary. There are a lot of things which are true for finite dimensional vector spaces which are not true for infinite dimensional.
Now, one thing that you could do is try and take a space of functions. Let's take V now to be the set of functions f from R to R, satisfying some property. Like what? Well, I mean, all functions from R to R, that's kind of crazy. There are all sorts of crazy functions. But you could take, for example, continuous functions. Or you could take f to be differentiable. There's lots of different
families of functions. All of these tend to be infinite dimensional.
I'm going to conclude this section with a little thought experiment, or pose a question. Actually, a couple of questions. First of all, suppose X is just a set. And I look at the set of functions from X to R. Is this a vector space? And secondly, let's turn it around. What about the functions going the other way from R to X? Same question.
So why don't you think about that for a moment and pause the video and answer both of those in your own mind, and then come back and see if you got it right.
Well, let's see. Is part A, is this a set? Is this a vector space? Well, I better be able to define addition and multiplication. So I better be able to tell you what f plus g of x is. If f and g are functions from x to r, what is f plus g? Well, you'd use this definition, f of x plus g of x. And this plus is in R, right? Because f of x is in R, and g of x is in R.
And so that defines addition. And similarly, scalar multiplication is Rf of x is equal to R times f of x. And again, this is scalar multiplication in R. So that at least defines the operations, and if you go through the steps that we did before, you'll see that this is a vector space. Now, if we look at B, what do you do? Well, you'd like to do the same thing. F plus g, you have to define addition of two functions. What's f plus g of x going to be? Well, the only thing I can think of is f of x plus g of x, and f of x is an element of x, and g of x is an element of x, and x is just some arbitrary set. It could just be a set with 2 elements or 100 elements or 1,000,000 elements, but there's no structure. And in particular, there's no notion of addition. It doesn't mean anything to add 2 elements of this set. So without that structure, the answer is no. This is not a vector space in any reasonable way. So let me conclude with one last example along these lines. What about the set of functions from a set to a vector space? And well, the point is that in a vector space you have addition. So you can make these definitions. F plus g of x is equal to f of x plus g of x, where this is an element of w, this is an element of w, and this addition here is in w. And is this a vector? Does this, with the similar scalar multiplication, is this a vector space? Well, the properties, if you go through the properties that you need, you'll see that since the corresponding properties hold in W, that this thing becomes a vector space. So one final word about this. What's the dimension of V? Well, this is getting way ahead of ourselves, but I can say a few words about it, and we'll come back later. Suppose that x is finite. So suppose that the number of elements of x is just a set, and it has some finite number of elements, m. And suppose that the dimension of this target space W was n, which is also finite. What does that make the dimension of V, whatever that means? Well, I claim that it's m times n, that there are essentially that many different functions in this space. And I'll let you think about that, and we can talk about it in class tomorrow. See you then.